In this video, we are going to discuss about the strain gauges. So by the end of this lecture, our core learning outcomes are to understand the fundamental physics of the piezoresistive effect. They can able to derive the mechanical and electrical principles behind the gauge factor and compare the different configurations of the Wheatstone bridge for signal conditioning and identify the primary structural types and biomedical applications of strain gauges in clinical as well as research settings. So what is a strain gauge? So here at its core, if a metal conductor is physically stretched or compressed, its overall electrical resistance changes because both its length and its diameter undergo physical changes. Alongside these physical dimensional variation, there is a fundamental change in the material's bulk resistivity that is called as piezoresistive effect. Because of this, resistive strain gauges are frequently used, that is called as piezoresistive gauges. Actually, in practice, they serve two primary roles. First, they are directly used for measuring strain and analyzing associated mechanical stress in structural or experimental testing. Secondly, they are widely integrated as vital secondary transducers inside other sensors, including load cells, torque meters, diaphragm, pressure gauges, temperature sensors, accelerometers, and flow meters. And the third one is gauge factor. So gauge factor, to quantify this sensitivity, we look at the gauge factor. Part of the resistance change can be explained by normal elastic dimensional behavior. When a strip of the elastic material is subjected to tension, meaning it is positively strained, then its longitudinal dimension increases while its lateral dimension shrinks. So as length increases and cross-sectional area decreases under positive strain, the basic law of resistance dictates that electrical resistance must increase. Here, experimental testing will reveal that the total change in the resistance is actually greater than what dimensional math alone accounts for. So this extra variation is actually directly to the change in underlying material under stress, that we call it as piezoresistive effect. And here let us formalize this mathematically by examining a strong gauge made of circular wire. Before any strain is applied, the wire has an initial length L, cross-sectional area A, diameter D, and a material resistivity rho. So this gives us our baseline unstrained resistance equation, R is equal to rho L by A. When we apply a tensile stress S, it induces a positive strain elongating the length by del L and narrowing the area by del A. Alongside, small shifts in the diameter will be indicated as del D and the baseline resistance will be indicated as del R. To mathematically map how the change in resistance relies on these physical variables, we differentiate our resistance equation with respect to the applied stress S. And by carrying out the differentiation and substituting Poisson ratio, which relates lateral strain to longitudinal strain, we can write our expression as dou D by D is equal to minus V into dou L by L. For smaller physical variation, this full relationship simplifies down to the following differential form, that is 1 by R dr by ds equal to 1 by L dou L by dou S plus V into 2 by L dou L by dou S plus 1 by rho dou rho by dou S. And it is very important to note that equation 2.12 remains strictly valid only when the piezoresistive effect, meaning the change in the bulk resistivity due to the strain, is negligible, which forcing the system to rely purely on dimensional changes. So single active gauge setup, because of these fractional changes in the resistance are tiny, we must use a Wheatstone bridge for precise measurement, And the first configuration is the quarter Wheatstone bridge. So here only one of the four resistors is in the bridge. In the bridge is an active strain gauge. When force is applied, the active gauge resistance shifts by del R, unbalancing the bridge and generating an output voltage V0. By applying the standard voltage divider formulas across the nodes Vc and Vd, we can track the exact voltage drop V0. So, given that the nominal resistance are equal, that is R1 equal to R2 equal to R3 equal to R4 equal to R, and knowing that the baseline resistance R is vastly larger than the tiny shift del R, the relationship simplifies elegantly to our final equation, that is V0 is equal to Vex divided by 4 into del R by R. So in half Wheatstone bridge configuration, in this setup we mount two active strain gauges onto a bending beam, typically placing one on the front face and one on the back face, because exactly half our four bridge resistors are now active sensing elements. This circuit is called a half bridge. Both gauges respond simultaneously to the induced mechanical strain, making the entire bridge sustainability more responsive to the applied force. When compared to the quarter bridge, this half bridge circuit yields exactly twice the output voltage for the same amount of strain, successfully doubling our measurement sensitivity. And the next one is full Wheatstone bridge. So in this arrangement, all four standard resistors are completely substituted with active strain gauges. This full bridge configuration enables the maximum possible voltage output for a transducer, significantly improving automatic temperature compensation, and it offers highest sensitivity of all configuration. Crucially, a full bridge circuit delivers a highly linear output because the output voltage is directly proportional to the applied force, with absolutely no mathematical abbreviations or assumptions required. So the types of strain gauges, depending on the application, strain gauges are manufactured in several major structural types. These are unbounded metal strain gauges and bonded metal wire strain gauges. Bonded metal foil strain gauges, which are highly common alongside vacuum deposited and spouter deposited in thin metal strain gauges. So finally, for applications required expectedly high sensitivity, we utilize this bonded semiconductor strain gauges and diffused metal strain gauges. So here we can see how the sensors are utilized within the biomedical fields. Three major clinical applications are there. One is gait analysis, where these strain gauges are attached directly to the various body segments to measure the real-time mechanical strains exerted on the muscles, tendons and bones during walking or running. And next one is prosthetics and orthotics. They are integrated directly into orthostic limbs and orthotic support devices for continuously monitoring the structural loading and the complex forces that is experienced by the device during the patient movement. And finally, pressure sensor in implants. They function as embedded micro pressure sensors inside critical medical implants such as cardiovascular stents or orthopedic implants to track the structural integrity as well as physiological load changes over their time. Thank you.